Good. Let's start. It's my great pleasure to have Christoph Englert here, who, despite his family name, is not related to Francois Englert, although I'm pretty sure that he told me once that he was, but maybe this was just a misunderstanding. This was many years back when he was still doing his PhD in Karlsruhe when I was visiting as a postdoc or so. So really many years back. And yeah, I'm very happy that he's here. He's an expert on BSM Higgs physics and all its varieties. And today he will talk about a mixture of Higgs physics, EFTs, touching upon G-2 and the connection physics at the LHC. I think this will be very interesting. Christoph, please share the slides and go ahead.
Well, thanks very much for the invitation. Nobody's more gutted than me that I can't be in Madrid.
Yeah, of course. This was my plan. Yeah, that you come to Madrid and we have a couple of beers together in the evening.
Yeah,
it was the original plan, but
living in Scotland on the West Coast in January is well, leaves something to to be desired for. I can tell you that. So Madrid, I'm sure, is much nicer than Glasgow for me. Although it's not a very bad day. So what I want to talk about today is pretty much things that I've been working on over the past few years together with people here in Glasgow, but also further afield. And it links a little bit to generic effective field theory interpretations of LHC data, and also going a little bit beyond LHC data. I hope that I have time for that towards the end, touching a little bit on G-2. Well, so where do we stand with that? And that's pretty much the picture of 2012, really, with Higgs discovery. We have in our theoretical tool set a whole range of ideas that we can use to construct solutions to issues that we still face in the standard model. But if we just take a snapshot of our understanding at the minute, in terms of what we think from a theoretical perspective, we understand very well how we can incorporate massless vectors and how they link to gauge symmetry on the divide between external and internal symmetries when you don't deal with supersymmetric theories. Really, that's the reason why we deal with gauge symmetries in the first place, or their key motivator, so to speak. We know how we can impart a certain fermionic mass structure into our interaction concepts that we see in the Lagrangian formalism in 4D renormalizable field theories. And with 2012, we also know that the non-linear realization of gauge symmetries is something that is realized in nature, and actually realized in nature pretty much as it was expected theoretically, but also experimentally when you look into Lab 1 and Lab 2 data. And a natural question for us to ask is really, what is the next chapter in this story? And the honest answer is really that we don't know yet. At least if you're a collider physicist like I am, then the answer is really not clear as yet. And of course, whenever you reach such a divide, then there are two possible avenues. And one is, of course, you focus on curing the theoretical problems that the standard model has, and they come in all sorts of sizes and shapes. Gravity is not part of it, etc., etc. Or you go back to the experimental drawing board and try to understand the correlations that we've seen or get reported really from the multipurpose experiments, say Atlas and CMS, try to understand them from a new angle and perhaps use those correlations as a guidance towards understanding what the next chapter in this story might be. And my talk today is sort of trying to interpolate between these two avenues and really ask the question, how and if and the circumstances of when effective field theory is an appropriate means to interpolate between these two questions. And I will use a bunch of experimental reference points to maybe give a general flavor of what my personal opinion is and how to move forward in that context. Because effective field theory, I mean, for those of you who are a little bit involved in the experimental program or in the collider phenomenology program, really is becoming the lingua franca of our field. And that has, of course, positive side effects, but also some limitations, and I'll try to highlight those. So what are the phenomenological limitations that we're dealing with when we employ effective field theory as means to interpret LHC data? What are the possible ways out for given limitations? And I want to focus a little bit on a theoretical problem that we know has to exist in nature, an additional source of CP violation, And the Higgs sector is a particularly well-motivated candidate to perhaps see that. And that also gives us another reference point to look at effective field theory from that angle. And then towards the end, as I already said, I would like to draw a little bit of a different angle on the G-2 excess for the muon. Please interrupt me at any point. Happy to answer any questions. Obviously, discussions remotely are always a little bit more difficult, but I'll try my best. So, fingerprinting the lack of new physics. This is pretty much where we stand with our understanding of the TeV scale. So we're really only at the beginning, because we have a range of LHC searches for exotics, but all of them really have results that are consistent with the standard model expectation. Perhaps G-2 is a particular point of reference for new physics, lepton flavor universality, and it's the tension with lepton flavor universality in flavor physics data is perhaps another pointer. But none of these things is really a concrete experimental pointer towards whatever new theory could think of. I mean, people build models around that, but it's probably fair to say that these are very, very purpose-built theories that address one of these issues, but not really going much beyond that. On the other hand, we know that the standard model is flawed. We know from the Sakharov criteria, we need an additional source of CP violation beyond what we see in the standard model. The electroweak phase transition in the early universe is not strong enough. We deal with hierarchies in the Higgs sector, which is more of a philosophical problem maybe, but still has been the direction of particle physics over the past 40 years. So, and I think that is still an underlying problem in our particle physics concepts. But if you take the LHC null results at face value, then we know, or we can set up a framework where we say that new physics, whatever new physics is there, is probably heavy and sufficiently heavy that we can integrate it out. So you can, of course, that's a general hypothesis in effective field theory. And of course, this will set the limitations of whatever I'm going to say. So it is, as long as you allow light degrees of freedom, then of course, there will be modifications of what I say. And also this will show up later on. So if you integrate these out, you can write down an effective field theory approximation, pretty much like the Fermi theory of the weak scale. And a lot of work has actually gone recently into the first collider relevant part of these deformations, which appear at dimension 6, and there's a whole range of them, depending on how you count them. There are 2,499 parameters. But of course, there are simplifying assumptions that you can make based on symmetries, as we always do in particle physics. On the other hand, you have concrete scenarios. So if you don't like effective field theories, you're of course not bound to study them, but you can look into concrete extensions, and there could be a 2x doubler model, could be supersymmetry, or could be more motivated approaches to effective field theory built on CCW sets, so ideas of compositeness, for instance. And of course, the idea of effective field theory, if you use that as a framework to interpret your results, is that at some point, they should lead to recyclable messages, in the sense that you can go on and you revisit your perhaps favorite theory through matching calculations in the way that you can reproduce or reuse and recast these constraints that are maybe provided by the experiments using the framework of effective field theory. So as I said, a lot of effort has gone into this particular dimension 6 analysis, and that's just a very, very busy slide to show you that this major theoretical thrust post-Higgs discovery, various groups have worked a lot on that and created essentially not only proof of principle cases and a lot of tools, but you can do it essentially just looking at the plethora of LHC data, and you can fit all of this often now also beyond leading order accuracy in various ways, using various fitting technology that's really out there. And there's enough proof of principle, I think, in my opinion, that the experimental ownership can now actually transition away from the theoretical community towards the experimental ones, especially because the tools are really there at a sufficient level. So perhaps now it's time to think a little bit about what is the value that we can get from an analysis like that, and where are the limitations, and going on from these limitations, what do we need to improve from a theoretical point of view. So effective field theory informing theory. So just one particular example here. I work a lot on the top sector and modifications of the top sector. And in many beyond the standard model theories, you typically have new top philic interactions. And that happens in 2x doublet model scenarios, in the MSSM as a prototype of the 2x doublet model, and so on and so forth. So that's nothing unusual. And you can just write down a relatively simplified theory that introduces a new scalar degree of freedom that's heavy. So it warrants integrating out. And it couples similar to the standard model Higgs. And essentially in any scenario that includes custodial isospin mixing, you will see such states appearing, coupled, of course, to modifications of the Higgs sector itself. So top pair production then is a large cross-section at a large hadron collider. It's one of the key processes that we study there. And you could think about really TT bar production as a laboratory to study the virtual presence of such states in the context when they are heavy and can be integrated out. So you can write down a whole range of Feynman diagrams that appeared next to leading order. And of course, the effective field theory hypothesis then tells you that this S-channel resonance has to be sufficiently removed from the energetic coverage of the Large Hadron Collider in order to verify or to be in agreement with the generic effective field theory axiom, so to speak. So you're not sensitive to direct resonances. Maybe you see the onslaught of a resonance, but actually you're only sensitive to deviations, small deviations that are modeled as polynomials in momenta and couplings. So if you integrate that out, essentially you squeeze this S-channel into a penguin that's given here. And that sources three relevant operators. So you get a chromomagnetic QCD operator. You get, it's actually one of the famous examples of flavor physics here. So you can use equations of motion for the gluon field to map this back onto for fermion interactions, and then study the anomalous coupling, the anomalous dimension matrix that way. So there are three relevant operator structures that are relevant to this matching process. And matching really matters here. So you have to integrate that out. And on the one hand side, you assume a certain coupling set and a certain mass spectrum. And then you integrate it out and you match it really to your effective field theory Lagrangian. You do this at the one loop level. So this is schematically given here, not too illuminating, but on the next slide, you'll see actually what effective field theory does. And of course, effective field theory is a tool set that works unless you somehow break its generic assumptions. So we have our full theory here. So this is the absolute value of the interference part. So we're only looking at the interference of your propagating S degree with the standard model. So that gives rise to a generic dimension 6 effect. So the lambda squared would be really the mass of the scalar here. And you see that over a broad range of energy, actually the effective field theory very, very nicely reproduces the full theory until you hit the S-channel resonance, for instance, in the gluonic channels here, which then creates, depending on how you model the width of your particle, a dip structure. And then, of course, you go into the S-channel resonance. And of course, this is also where you would lose predictivity of EFT simply because that theory doesn't know anything about that propagating degree. So now there's an additional, I wouldn't say issue, but where limit setting appears or where limit setting is driven is usually a phase-space region where your hypothesis is well modeled. So where statistical control is good, but also uncertainties, both experimentally and theoretically, are small. And that's typically at low momentum of these tops. So when the tops are not very, very, not produce a very large transverse momentum in your detector. So this will actually happen here. And if you just employ the naive limit setting that we are doing now, where you maybe don't really have so much control over top pairs that are produced at large invariant mass, then you would actually be drawn towards a different power scaling or a different power counting between these different operators from the first, from from the get-go, essentially. So in a naive effective field theory approach that we would use, for instance, in our top fit, you would just fit that data here, that little excess that you see, and you would predominantly address this to a chromomagnetic deformation rather than a loop-induced four-top interaction, which this really is. So you integrate out that additional scalar that gives you an additional four-top interaction that then sits in the loop and radiatively generates your modifications at low PT. So a way out is, of course, that we get the full information from the experiments, which is difficult to do. And of course, there has to be a little bit of a crosstalk between experiments and theory, but it's also really the reason why I think that you do this in-house in the experiment. You don't really necessarily deal with shortfalls of that type. So matching is really crucial. But what's also crucial is that we need to see some deviation in order to disfavor the standard model. And that has to happen in a way that it doesn't really break the intrinsic assumptions of our perturbative means that we are using here. So we need to end up with limits in a range where we can still match it to some ultraviolet theory in a way that it's perturbatively controlled. If that doesn't happen, then the process is really invalidated right from the start. And TT bar, albeit high production cross-section and lots of statistical control, when we move to the high luminosity LHC, we'll have plenty of data there. But uncertainties, predominantly from a theoretical perspective, can actually really spoil the day. So if you look at what happens now, if you look at TT bar extrapolations, and maybe also include four-top final states here, which are sensitive to such a nested four-top interaction when we integrate out that additional scalar, we can ask the question, looking at uncertainties that we expect there, where do we end up with limits on from the effective field theory onto the ultraviolet model that is consistent with the generic assumptions of EFT, namely that this S is sufficiently heavy, that it's not seen as an isolated resonance. And when you do this here, you'll see actually in the top sector, this is a very, very delicate thing. So the blue box here is really unitarity, unitarity in the context of this propagating S. So you can look at partial wave unitarity in TT bar scattering, but you can also look at the width of that additional scalar when it decays into tops. And when that becomes comparable to its mass, then of course you're losing unitarity, because that's just essentially Katkowski rule. So you can see that this particularly is well modeled here in four-top production when you lose sensitivity because that S becomes so wide and you don't really produce it anymore. It just tells you that it's a generic breakdown of perturbativity at that stage. And the bad bit really is that we see agreement between full and EFT calculation, of course, as you should. Yeah, so the solid line is you use the full propagating result, the EFT result is dashed. But that sits somewhere where you actually have lost unitarity. And that's not really a breakdown of effective field theory. As a matter of fact, effective field theory works brilliantly. And the agreement that you have between these lines will be there. So it's not a problem of effective field theory, it's a problem of the uncertainty of TT bar measurements that we can expect at the Large Hadron Collider. So if you were able to improve the sensitivity with which you can measure these, then actually what would happen is that both these curves, they come down, you would be able to move them into a regime where you can actually perturbatively match effective field theory measurements and concrete ultraviolet scenarios. So in this context, there are three things that we need to keep in our minds. So new states need to be heavy compared to the probable energy scale. So the LHC has a vast energy coverage. So we probe very, very large invariant mass TT bar pairs. But at the same time, we need very, very good precision over low invariant mass TT bar pairs or any collider observables in order to really see these effective field theory approaches prosper. So BSM deviations still need to be large compared to that uncertainty, and that's often a thing that's forgotten. And that really can show its nasty face later on when you think about how to reuse these effective field theory constraints that we would construct ab initio, really from LHC data, and then contrast them with concrete ultraviolet scenarios. And the custodial isospin mixing that I showed here is just one example of that. I should add that this is a very, very process-dependent statement, but at least in the top sector, this is very, very difficult, okay? Because uncertainties are very, very hard to control here. But the reduction of uncertainties is really crucial. So what are the ways out here? So it's coming always back to the original question, really, in particle physics, is how far uncertainty is limiting factors, and what are the ways to mitigate that? On the one hand side is very, very classical, and to some degree also very, very German attitude towards treating problems related to precision, is that using loop calculations, multi-leg calculations, and various ways of resumming stuff. And that has given us quite a little bit of sensitivity reach. So top quark pair production is now known at n square LO. Higgs pairs, Higgs production is known at n cubed LO. And Higgs pairs, for instance, as additional candles of BSM interactions are known now at full next to leading order, introducing the top mass threshold really as a finite concept there, which is important. So that's one avenue with which you can increase high luminosity LHC sensitivity estimates. But of course, the techniques that we are using there might not scale, and the development here is typically not slow, but it might not align with the needs that we have, given that statistical uncertainties will be small, or are already small in many, many channels. So at some point we'll be theoretically limited. So what do we do in such an instance? Then we can perhaps pursue a second avenue, and this is very much an avenue that I would like to focus on in this talk. So we can look into more robust ways of classifying beyond the standard model interactions and really tell them apart from standard model type of signatures. And that can use data-driven techniques. It can use machine learning as really approximations to more general likelihoods. And we can use anomaly detection as well, but I'm not going to talk about anomaly detection today. So what are the prospects now for hunting new physics in run 3, trying to pursue perhaps that additional or slightly less precision calculation driven avenue? So when you look at these deformations at dimension 6 level, they typically impart a rich particle level event structure. So you end up with high multiplicity final states in the Large Hadron Collider. Those are very difficult often to improve from a perturbative QCD point of view, but we can perhaps use some techniques that remove some of these perturbative uncertainties. So what we want to end up with essentially is a way of classifying new physics from standard model physics without being sensitive to the underlying uncertainties, whatever their origin might be. A classical example for that is Higgs production plus 2 jets from gluon fusion. So it's a multi-scale problem in QCD, so very difficult to calculate, and so far only known to next to leading order precision, and that in the effective field theory limit. So you produce the Higgs in association with 2 jets, so which will be 2 collimated splashes of hadrons in your detector. And what Kempel, Ellis, and Zanderriege did in 2006 is they integrated out this top quark here, just giving a contact interaction of the Higgs with the gluons, which in its own right is a dimension 6 operator. And they did that because it's known that this M to infinity limit is actually accidentally good. So we know that the distributions are quite well modeled by that. And then this additional top mass does not really introduce a Compton wavelength that your QCD would be so sensitive to. But of course, if you now allow for these different coupling modifications in the Higgs sector to appear, you can change the interaction of the Higgs boson with the top quarks. You can introduce maybe a heavy top partner, integrate that out. That would typically appear in composite Higgs scenarios. And then there can be competing effects in such a way that those two new sources of beyond the standard model physics are pulling in opposite directions. And that's also really manifestly present in composite Higgs scenarios as well. They're just set up to do exactly that. So when you now look into the distribution and try to really tell these two interactions apart. That's a question that is as old as particle physics in its own right. You'll have to inject an additional external momentum scale that can tell a difference between the intrinsic Compton wavelength of your propagating degrees of freedom and their absence. And this is exactly done by producing that Higgs at a finite and large transverse momentum in your detector. And then above that, you will see a deviation, even if the entire rate of your production cross-section looks standard model-like-ish, then you can really tell these two sources apart. And given that we have quite a good understanding of how QCD works in this particular sector, we can come up with good scale choices in the sense that we are evaluating alpha S and the PDFs here at a good or well-motivated scale choice. And that really absorbs a lot of the uncertainty already and shifts that really into the overall rate rather than in uncertainty of the distribution. So how would you be able to tell these things apart? So you can, for instance, look into machine learning for that, and you would really start throwing different observables or perhaps very, very high level input into that, 4 vectors, you name it. Doesn't really matter for what I want to say. So you just look into a certain set of observables and you let the network or your boosted decision tree decide which one of these is more suitable to tell apart the standard model from a deformation of the standard model. And that will quite naturally focus into a very exclusive region of phase space where the deviations are large, but where there are very, very few events. And that can be, for instance, here in the tail of that distribution. So that's the most natural phase space region to look into to really tell apart standard model from a cancellation of these two interactions. So there are different ways, of course, when you set that up. And this is a particular network that we wrote just to show the impact of uncertainty. So when you start fluctuating your standard model distribution within that gray band, then of course the limit that you set, or the susceptibility of your ability to tell apart standard model from BSM, is really, really harmed. And you can see this by looking at the neural network score. So your neural network will decide new physics should go into a score of 1, and good old boring standard model should go somewhere to 0. And then if you start varying the standard model uncertainty, you'll see that the overlap of these contours, which really is a confidence level of an event, or a certain sample being non-standard model like-ish, that is really, really highly vulnerable to scale choices. So, and of course we know that scale choice should actually not matter. But what the network has learned really here, more or less, obviously, is the regions that the classification into BSM and SM is particularly affected by scale uncertainty. So you can use that in an adversarial neural network to penalize the classifier in such a way that you tell the new physics versus old physics classifier that it should not discriminate between the two if you don't understand your null hypothesis there in the first place. And this goes under the headline of adversarial neural networks, as I already said. And if you switch that on, you'll see that actually remove the distinction between uncertainty bands here entirely. So you end up with overlapping standard model null hypothesis at the price of a not so ideal discrimination between standard model physics and BSM physics. But you do that in the most robust way. And that's one way of mitigating uncertainties that we see and that we know have to be there in collider physics, is essentially avoiding them or trying to plot a route around them using techniques that really incorporate uncertainties right from the onset into the very definition of an optimized observable. So you can see really that correlations in data are very, very important, and controlling them is very, very important to maximize the BSM potential at the Large Hadron Collider. And in theory, we know, as long as we're dealing with perturbative physics, we know that all correlations are very, very well modeled by Feynman diagrams and Feynman graphs. So they include kinematic correlations, so we know exactly how the top quark should decay in a statistical sample, how it will appear in terms of helicity correlations. We know what the color correlations are. And then the whole idea of collider physics and the task for our experimental colleagues is just to essentially reverse engineer that whole process. So you start with infrared safe and particle level observables, and you reverse engineer them into collider observables that exactly allow you to, at least to some degree, allow you to reproduce these correlations and then use these correlations to tell apart new physics from standard model physics. And the question that we asked here is in a recent paper, I think from the end of last year, is, can we actually cut out the middleman? Can we cut out or make this reverse engineering a little bit more efficient? And what I mean with that is, can we actually impart a Feynman graph type of correlation onto the definition of observables and then onto the measurement itself to enhance BSM sensitivity? And a technique to do that, or a set of methods to do that, goes under the headline of graph neural networks, and those have been used in various guises in different areas of particle physics since the I would say probably since 2018 as classifier problems. But every bit of data that has a certain graph structure, for instance, the way how we combine these hadronic splashes of activity into jets, which are well-defined theoretical object, that has a certain graph structure, it has a certain metric, and people use that in the context of graph neural networks to tell apart QCD jets from W-induced jets or top jets, for instance. So that's work by Dreyer and Hu in 2020. We had a look at general anomaly detection. So when you look at graphs and how QCD shower evolves, how high velocity quarks sort of fractures and produces splashes of directed radiative activity in your detector, you can use that and its graph structure to tell that apart from the understandable particles as well. But what I want to show you here today is using this really as a way to enhance effective field theory fits in a high multiplicity final state, such as TT bar production, and here look into semi-leptonic TT bar production, because that is a little bit more transparent what's happening here. So we did this late in 2021, so all our students and my colleague David Miller is involved in that as well. So it was a little bit our lockdown project, so to speak, trying to shoehorn a little bit more sensitivity into parameter fits using neural network techniques, and in particular these graph neural network techniques. So what's the idea? The idea is that you have a certain selected final state that you would attribute to semi-leptonic TT bar production. This is something that experimentalists and theorists have done for decades. So more or less with some level of purity that you're dealing with TT bar production, okay? So each individual final state that you see is then associated to a node of a graph represented neural network. So your lepton from one of the top decays is a node. Your jet from the other W decay from the top is associated with a node, and so on and so forth. And you give these nodes features, and these features should describe in a way that we can address them, at least experimentally, their location in the detector and their characteristics, so to speak. So particle ID, transverse momentum, the calorimeter cell that it hits it, and the energy deposit, and depending on the PID, that's also linked to the mass of that. Then you introduce edges between these nodes, which is essentially a message of correlation. So just tells you how are these nodes correlated. And one particular graph that you can then reconstruct or motivate or give the data to decide whether that's a good graph in the sense of correlation or not, is one here that really reproduces the TT bar decay. So the top decays into a bottom, then it radiates of a W, that W will split up into missing energy and the lepton, and the same here for the other top. And so this shows you that this graph structure that you would find motivated from the normal TT bar standard model production, so to speak, and its decay all the way down to the particle level in your detector, reproduces a little bit that Feynman graph structure that I alluded to earlier. So you can use that to reconstruct the W or tell apart for fermion interactions that are naturally part of the dimension 6 extension of the standard model. So you can look at, for instance, a heavy W, you integrate that out, you'll actually end up with something that has not a W node. So you see different graphs appearing depending on whether you deal with the standard model or the standard model plus something else. And effective field theory just tells us that this something else could be everything. So then we use supervised training over all graph structures to enhance the BSM sensitivity. So that's the idea, which really means that we are looking into graph structures that are motivated from the data meaning that we are looking into dimension 6 deformations of standard model data, and then really let the network decide what are the important graph correlations that we can use here. So that's not an easy task in first place, because if you look at the leading order deformations here, so dimension 6 level, and only interference with the standard model, that would come at this interference contribution. It looks like that. So you start with the standard model amplitude, you construct the dimension 6 amplitude, and then the dimension 6 leading deformation of the amplitude squared is given by this interference piece here. And in semi-leptonic TT bar production, you get already 13 relevant operator structures. So you deal with quite a few interactions. And this is also the reason why, if you just do it agnostically, you will actually end up with very, very poor constraints on your EFT parameter space, because typically you will not be dealing with 13 independent measurements of that channel. Okay, in a way, when you include stuff like that, then of course your distribution is also modeled as a well-defined polynomial. So there's less information in differential distributions than you might naively anticipate. A lot of that is really already constrained at relatively low PT. So what's the traditional approach that we want to compare things to? I mean, at the end of the day, if you do something like this, you want to make sure that you gain something rather than just adding additional layers of complexity. So the traditional approach would be that you identify a fiducial region and you do a multi-dimensional fit to differential distributions that are available. And here we use a relatively old CMS top analysis that provides a whole range of distribution, also double differential distributions. So that defines our sensitivity baseline that we want to improve on. So what happens now when we look at graph neural networks? So for the machine learning improved part, this means that we have to deal with a discrimination problem in a multi-class environment, meaning that we have 14 relevant IDs, so to speak. We have to include the standard model into this counting as well. So we have 14 classes that we need to discriminate between. And if you use just bulk standard machine learning, you'll get out at the end essentially a 13-dimensional probability distribution, so to speak. Neural networks only know about probability unless you feed cross sections in it. So it'll just give you a probability of a certain event belonging to one of the 14 classes. And of course, they are correlated in such a way that they have to sum up to unity and probability. So you deal with really 13 independent probability distributions that are relevant. So you could think, I'll have my 13-dimensional observable, so to speak, and then I'll just cut on that and set a fit up on the basis of the neural network score. However, that doesn't really scale with data. I mean, we have a lot of TT bar data, but if you start building up that into like 13 independent directions, you will start to lose statistical sensitivity very, very quickly. And that actually happens here at 3 inverse autobahn in the top sector already when you introduce 3 operators. And you can see this, first of all, you see an improvement, which is great, which you should see. So that the black curve here is the inclusive selection, just fitting that data. Whereas the pink one here is a 2-dimensional histogram score that really distinguishes the standard model from these 2 operators, and what they are doesn't really matter for this here. This additional green curve here is a separate approach, which does not really link to the direct neural network output score. So you can see that whatever that is performs more or less equally well. So what is this? That's a fit that's essentially based on minimizing the overlap with the standard model class. So we're looking into events that the graph neural network identifies as non-standard model like-ish. And then we use that as an input to the traditional fit. So we essentially correlate the neural network output score with the observables that are provided in this analysis. And that will allow us not only to reflect the correlations that the graph neural network has learned, but it will also tell or superimpose that information on how these different observables are linked together. And then you just run a traditional fit in that sense, adding this additional neural network output score as an additional guideline for the fit, so to speak. So scalability is then really reduced to the operator multiplicity. So then if you have a framework that runs with 13 relevant operators, in principle, it can also run with 14. Of course, not forever, but I'm confident, or we are confident, that we could, for instance, include the dimension 6 squared effects here as well. So that would be formally of dimension 8. But the graph structure will actually pick that up, because the resonance structures will become easier for these particular contributions. But that's just a side remark. So what is it that we gain here? And we can see that there's a whole range of improvements that we can obtain in that approach relative to the baseline sensitivity that's given here by CMS. So I just highlight 2. So you have 4 fermion interactions, which are actually improved by almost 70%. Interestingly enough, if you look into profiled constraints, where you essentially get rid of some of the other directions in the fit, you get higher sensitivity, and we can understand where that comes from as well. And you have operators as well. So Cbabu, that would be anomalous gluonic interaction, so a new contribution to the gluon 3-point function, for instance, that has almost no sensitivity improvement. So why is that? Well, large improvements are attainable when exclusive phase-based regions are really affected by that, and the neural network score learns that, and the way the different nodes in the graph communicate with each other, they will pick that up and will tell the traditional fit, this is something that you need to take into account. And this is where the 70% of improvement come from. So for Cbabu, there is no improvement, but that really is a modification that affects pretty much the entire sample. So you see, you don't really rely on 2 exclusive regions of phase space. This is really already modeled by the inclusive cross-section, so to speak. So splitting things up into bins, whatever kind of shape they might have in phase space, doesn't really gain anything, because the fit understands that their collection really is the driver behind it statistically, but also through the lens of uncertainty. What happens now with these profiled results? Well, you get an increased sensitivity here because we are minimizing the standard model contribution. We are not really tensioning any of the new physics operators against each other. So we end up with selections there where some of the operators do not really, pull against each other. And this then gives you a higher increased profile sensitivity. So that is something that we would use in theory, because of course, as I showed you in the earlier TT bar example, different theories come with, different power counting, come with different matching coefficients for different operators. And this you can really impart in a methodology like that by tensioning or redistributing different probabilities into your final fit. So there's quite a bit of scope to improve that. And that I think this is quite promising, and of course you can hope to spin this out a little bit further in the following year. So coming now back to my second point, model independent CP violation is also modeled by this guy here. So why is this a relevant question? So it falls a little bit away from the TT bar discussion that I had. Well, Atlas already saw something that looks a little bit like CP violation in 2006, and they looked into Z+2 jet production in a weak boson fusion channel. So that's essentially just electroweak Z+2 jet production. And they specifically looked into asymmetry measurements. And those asymmetry measurements, they have the benefit that CP even effects just cancel out in these. But of course, it's very challenging there to combat fluctuations, and it's always experimentally challenging to get rid of unphysical asymmetries. What they found here is that actually this operator here, that is the CP violating operator that links the W fields and the B field in the gauge basis with the Higgs field, is favored to a relatively large value that really more or less excludes the standard model with that p-value here. So there are 2 questions here. Of course, when you see that, is that new physics? Does it make sense to understand that as new physics? And perhaps more importantly, why is there a dedicated difference in data between these two directions, because they are formally of the same dimension 6 quality. Naively would expect the same sensitivity here between the two. So that already shows you that something's odd here, and perhaps it's difficult to create a theoretical situation where all of these are actually produced like that, the Wilson coefficients. So the size of these Wilson coefficients are so large that it's very unlikely this is new physics, but it's testable. So you can look into W gamma production, for instance, which is sensitive to these two additional operators that Atlas are considering there. So that region is favored by Z plus 2 jet production, and essentially this region could be cross-checked with W gamma production, which is essentially sensitive to only these two operators at leading order. So there are ways for EFT to tell you here, this is something that we can cross-check, but perhaps more importantly, when this excess will be gone, what is the take-home story? What is it that we learn from it? Atlas are assuming here 2 parameter CP odd fit, and naturally it goes a little bit against the grain of effective field theory that you say, like, we are limiting ourselves just to 2 operators in this space where you could have many more operators. And the question that we asked them together with actually Supratim Dasbakshi, he's now one of your colleagues in Granada. So if you want to know more about these things, you should invite him, not me. You can find theories where these 2 parameter CP fits actually do make sense. And it's a very broad class of vector-like leptons. And there, these 2 operator structures are the ones that are sourced. And actually, you also have a power counting in these theories where, at 1 loop matching, you would only introduce this operator in Z plus 2 jet production, and this would actually be 2 loop suppressed. So you have something like a STU argument, but not really from the dimensionality type of counting, but really more from a loop counting approach. So, and these broad UV assumptions then reduce the complexity of the fit quite dramatically, thus enhancing the sensitivity again. And this is also robust to considering dimension 8 when you include that in the matching. And that really boils down to what we already know in the standard model. So when you have one source of CP violation in a concrete theory, then it will reappear in every CP odd observable or matching calculation as such. So unless you're introducing something completely new at dimension 8 in an effective field theory type of approach, this would not be sourced in this ultraviolet theory, at least for this particular one that we have here. So the question is now, given that we can perhaps make some sort of understanding of 2 parameter fits, so relatively low few parameters, can we even get more sensitivity out of that? And this really takes a little bit the interference and asymmetries at face value. So if you look into CP even observables, like the cross-section, they will, as inclusive quantities, will never tell apart different CP violating phases or effects. But what you see is a dedicated cancellation between event weights that are characterized by different CP quantum numbers. So the question is, and that's the question that we tried to answer in December last year, together with two people from the Atlas experiment. So that's my postdoc, Akanksha. She worked. I mean, I'm at an age now where I can take credit for work that's been predominantly done by others. So, but I'll try my best to not do it too much. So the idea is really to create an optimal observable that really distills the sensitivity out of the event weight. So what has a positive sign, what comes with a negative sign, and then you construct a discriminating observable around these. And we looked into 2 different cases that are different but well motivated in the sense that CP violating signatures are well understood there. So one is Higgs to ZZ production, and you can look into a decay plane correlations between the leptons of the Z decay. So this is well understood years ago in flavor physics, and you can really set around that in a neural network, and this will tell you how important are these different angles, for instance, and how do they link to other information that you can construct from your top level information. And you can see that this phi 4L, which is really the relative plane angle that you can construct from these leptons, from the Z decay, they are massively important. But at the same time, also the reconstructed Z mass is very important. So that would be the heaviest Z, which at sometimes really reproduces to the physical set that goes into leptons. Then there is a dedicated change in how the weight behaves as a double differential function of the Z mass and this particular angle. And if you use that, you can actually enhance the sensitivity in your CP fit. So if you use that, then just on the basis of this Atlas 4L analysis from actually last year, you can enhance the sensitivity by really, factors of 2 in directions where you have already a little bit of sensitivity, and you can enhance it even better in other directions. So if you really use additional information there, and that additional information is really condensed down through the neural network. So there's something else going on here. So this binary means in this context that it's +1 versus -1 weight in a way. And there's multiclass as well, where you inject the standard model on top of that, and that becomes relevant when you look into Higgs+2 jets, where you really need to tell the neural network that there is some additional distribution other than your traditional delta phi JJ angle, which is a very, very well motivated observer to tell apart different CP hypotheses of these contributing operators here. And if you do that, then you gain sensitivity predominantly to this particular operator. There is a modification of W field strength in the gauge basis. The others are relatively flat, and that's known in the literature. It really comes from the fact that W interactions are more important in Higgs+2 jet production in weak boson fusion. So there's a general thumbs up, which really gives you a sort of a practitioner's approach to improving CP measurements in the future. So I don't know how much time I have left, or if
maybe 1-2 minutes.
Okay, so I'll be quick.
Depends how interesting it is what you ask.
Well, I'll say a few words about G-2, and obviously the anomalous magnetic moment is part of this dimension 6 Lagrangian here, so it is an interesting quantity in its own right to study here. So it really boils down to looking at the general 3-point QED vertex, and you have the normal vectorial interaction, the G-2 type of interaction, and on top of that in chiral gauge theories, you have additional contributions here. And the magnetic moment can just be looked at by evaluating this F2 form factor at zero momentum transfer, whereas the electric charge is really determined in the Thomson limit. So you can directly, essentially in any ultraviolet complete extension of the standard model, G-2 becomes a prediction because it's dimension 6. And it's such that, of course, there's a QED offset, alpha divided by 2 pi. Schwinger calculated that famously in 48. And now people are evaluating this really at 5-loop level in quantum electrodynamics. So tremendous progress. And the power counting is such that the muon is really ideally placed to see something if new physics is there, because whatever x runs here in the loop, it enters in the denominator, and the mu is large enough that you could see something. The electron is, of course, too light, but measurements using Penning traps, for instance, show that there's large error bars, but in principle, good consistency with the standard model expectation, whereas the tau is really decaying far too quickly for such a measurement to take place. So the muon is really well placed, and of course, you know that there is a deviation, and there has been a deviation for quite some time. And that deviation is mostly related to how we understand the standard model prediction using dispersion relations, so using E plus E minus to the R ratio to jets, essentially to quarks, and then using dispersion relations to map that to G-2 in the hadronic vacuum polarization contribution to G-2. Of course, there's the BMW result in 2021. So I think the jury is still out there discussing whether that's a flaw in the way how we calculate this, or whether it's new physics. But I'll take a new physics angle on this. And of course, people have been trying to look into different potential UV scenarios that go beyond the standard model. They can produce that. And it's probably fair to say that none of them is really doing the job very, very well. So for instance, type 1, type 2 Higgs doublet models or supersymmetry It's challenging to do this in a traditional way. You have to use some kind of flavor specific flavor alignment to address that, but then that will also give you testable implications for the LHC13. What I try to do here is take a slightly different approach to that. So is there a way out of this perturbative conundrum, somewhat inspired by composite Higgs scenarios, where a weak interaction that links the standard model with your beyond the standard model sector? So of course, you have full multi-loop calculations, and there are many examples of that in the literature, and I'm sure Sven is more than happy to give you a talk about those as well. What I'm trying to look at here is, it has to be either strongly coupled or it has to be light. So, let's buy into the strongly coupled part, but assume that the strong coupling really appears in the BSM sector. And then, of course, you have two different kind of methodologies that you can use. So you can treat the standard model plus the extension as an effective field theory. And that elevates G-2 to input data, pretty much like the Fermi constant is an input to the electric standard model. And then you can ask the question, what is the precision that we gain from G-2? How much can that inform an ultraviolet completion if you buy into G-2 becoming an input parameter of your theory? And you can actually reach something like 100 to 200 TeV, so very, very far outside the energetic coverage of the LHC and any future collider that we can even dream of technologically. So what I'm trying to do here is I'll try to discouple that a little bit, but say strong interactions happen in sectors that we don't know, and perhaps also linked to sectors that we don't quite know as well yet. So that is the Higgs sector. So if you do that, you can actually extend your standard model sector with additional propagating degrees of freedom, thereby addressing some of the standard model shortcomings beyond G-2. And that's really built on the idea that masses of particles is something different than cutoffs. So GF is really a cutoff, and it's vastly different from MW, which is a mass that really ultravioletly completes GF, so to speak. And then we can reflect any integrated out dynamics that such new states might have. And it's a little bit interpolating between effective field theory and concrete ultraviolet extensions. So we look at a particular scenario here because it will serve exactly that purpose. It's the Cbabu model. We have a doubly charged Higgs and additional singly charged Higgs. And it's been known for years, decades, that this creates a negative contribution to the anomalous magnetic moment of the muon just by evaluating these Feynman diagrams. Now, if you look into all possible deformations that such a theory can produce, you can actually overcome this at strong coupling in a way that scale suppression gets partially cancelled out by kinematic enhancement. So in effective field theory, you'll essentially feel the velocity that runs in this loop, and that might actually circumvent some of that mass suppression that you see here. So when you start off, of course, you will source ultraviolet divergences in this dimension 6 operator, but our hypothesis is that these are really linked to radiative effects of this additional strongly coupled sector that links the Higgs sector with the new degrees of freedom. And there, actually, the analytical result is manageable, at least for the doubly charged guy, okay? And we have the full expression in the paper. It doesn't really matter for here. So just to make a little bit of progress, it seems a little bit artificial. Why are we choosing this particular scenario? Well, it turns out that the phenomenological overlap of Higgs physics, direct production sensitivity to these new exotic states, and the anomalous magnetic moment is very, very small. So you have only two operators that matter here. So it becomes very, very predictive, of course, at the price of being model specific. So what's the upshot? So there's an excellent opportunity to tell that apart, and that's just motivating approaches like that a little bit for the future. We are not just looking at effective field theory in the context of the standard model, but perhaps introduce an additional propagating degree of freedom that can then tell you something about where that ultraviolet scale could sit. So we have a deviation. So of course, the Fermi-lab result is different from the standard model expectation. So this would be consistent with the white paper. And you can see if you now include direct sensitivity to a Higgs pair production, charged Higgs pair production as an electroweak process at the LHC, you'll be able to completely tell apart what's happening here, okay, on the basis of the existence of this additional degree of freedom. There's some blind directions as always, because at the end of the day, you're only sensitive to charges here of stuff that runs in the loops. So you can manufacture a situation where there's a cancellation between these degrees of freedom, but then again, you can go back. So there's a viable region when you look into the Fermilab result and Higgs data that is, mutually described by this scenario. But then you can directly exclude this with direct searches at the LHC as well. So you can really pinpoint the existence or non-existence of that relatively straightforwardly, in particular because this is a very, very simple search. It's just essentially fitting a background and looking for a bump. So summary, I'm running a little bit late. I'm sorry, I'm not very good at these remote talks. I think EFT is a versatile tool for new physics searches, but it really is a tool. It's not, I mean, people tend to propagate it a little bit as like the new step in theories. And I think that's slightly wrong. It's a tool, and sometimes you need to think about which tool is appropriate for what. So you can't buy a spanner from from your supermarket and try to fix your Swiss mechanical watch with that if you are lucky enough to own one. Okay, so but there's rapid development in how we can match certain theories to the effective field theory. People are discussing this beyond dimension 6, which is interesting in its own right due to positivity and analyticity as well. So you should talk to you're probably talking to your colleagues in Granada about that anyway. But really what's important is that EFT assumptions do not balance very well with the expected energy coverage that we can get at the LHC. You're removing new particles to beyond what the LHC can probe for that to be a valid approach. And then uncertainty can come around the corner and really bite your bum. So in order to mitigate that, you have to come up with more sensitive analysis approaches, or perhaps buy into some interpolating picture between concrete ultraviolet scenarios that reduce the complexity of your EFT fit, thereby enhancing the sensitivity. That's all from me. Thanks very much for your patience. Sorry for running over.
Okay, Christoph, thanks a lot for this interesting talk. Although indeed it was a little bit long, but I'll forgive you.
You can cut it out from the recording.
Yeah. Are there questions or comments? You know that remotely this is always a bit complicated. I have at least two questions or comments, and yeah, maybe I start and then we see whether people dare to ask their own ones. First, a more practical one. When you say, for example, you developed this new strategy to enhance the information to get in this, for example, CP analysis, yeah, that you were showing in the last part of your first large block. And the improvement seems substantial, yeah, from the numbers that you are quoting. Do experimental groups pick this up? Do you talk to them? I mean, you have close connection there in Glasgow to Atlas, as far as I understand. Yeah, they must be highly interested in this. So how does this work out?
I think the top stuff is relatively new, and it takes a little bit of time to to be completely fair. It's also not, how that will be affected by uncertainties is a completely different story then, right? So you have to sort of go back to the drawing board on that front as well. So that was one of the, it's a proof of principle analysis on that level. But I think in principle, it can be done, and it could probably be even better done in an experimental environment because they know better how the correlations work, and they have a better estimate of, for us, this is assumptions essentially. For the Higgs stuff, I know that the 4L people are talking to Andy Pilkington, who's on that paper as well. So they're interested in pursuing these things. And this is also why
they should be, the experimental analysis, the experimental groups should be interested in improving their sensitivity.
Yeah, to be honest, between us and the 30 other people that are connected here, this is also why we turn to like relative improvements in papers now rather than absolute values, because that shows what's the margin of improvement rather than what is the number. In effective field theory, a number doesn't really matter so much because it's a ratio.
Okay, well, good luck with that. Yeah, I hope. No, it's serious. This was meant very positively. I hope this works out. I know how difficult it can be to get the interest of experimental groups when you think that you've done something that can be helpful for them. I have another question on the G-2 stuff, because there I'm always, I mean, I see in general virtues that EFTs have, but particularly for G-2, I'm not sure whether I fully see the virtues. I mean, you are even mentioning this, you can probe scales up to 200 TeV, of course, yeah, this is, if you assume that everything must be very heavy and the couplings are of natural order, something like this. On the other hand, I know that in my SUSY models that I was looking at, we have scales of 200 GeV, not TeV, and we get a good fit to G-2. Yeah, so I think naturally, if you have lighter particles in the game, which makes the application of EFT in this context more complicated or questionable. But still, you seem to have done it, and with some.
Yeah, I agree with everything you say. That the paradigm here is that new physics should be light, and that was the starting point of us to like reintroduce new degrees of freedom. And it was, perhaps a little bit ill-advised to look into something that you already know. You have to overcome a negative contribution. You have to overcome it in such a way that it also creates 4 sigma, a new physics effect. And possible though, because there are logs in the game, and you can achieve that, albeit at strong coupling, and that will tell you then correlated results with other stuff as well. So I think what I showed here was very, very specific to that particular scenario, which is not necessarily so motivated from a G-2 perspective, but motivated in other parts, in neutrino physics and the like. And so that gave us enough of a motivation to try and see what happens. And then we were quite, I was amazed to see that actually, if you look into Higgs physics, exotic searches, and G-2, that you essentially end up with one overlapping direction. And that can be fully pinned down with a very, very simple search, which of course, all of this is subject to the assumptions that we have of the particle spectrum.
Of course.
But I think that you can bring down additional degrees of freedom. That I don't think that's excluded in any way or form. We see that in the standard model already. And I think I said this during the talk, you have GF, which is the cutoff of the electroweak standard model, where something gets strongly coupled, but the W mass kicks in much earlier than that. So you can have new degrees of freedom and still a cutoff that is considerably larger than your new propagating degree of freedom. That's possible. So masses are different to cutoffs, and I think perhaps there's additional freedom. If you only look at the standard model effective field theory, you might actually miss, well, by definition, you are missing that, as you say.
Okay, good. Yeah. When you presented the example model that you're looking at in this context, was it already a little bit unusual to have one model that normally predicts even something worse than the standard model? Yes, which makes it more challenging. Okay, good. Yeah, I do not see more questions, but I said this is this Zoom environment, as I know, is not
worries.
ideal for this. And next time we'll arrange it in a way that you indeed come to Madrid, and we'll all appreciate this.
I'm looking forward to that, believe me.
Yes, definitely. I'll send you a message about the Higgs days 22.
Cool.
Let's stop it here. I stopped the recording.